Hi, this is Bailey Chapin, and this is my Physics 1 Lab 1 on constant velocity. First, we're going to look at the introduction and the purpose of this lab experiment. The purpose of this lab experiment is to observe the motion of a moving object. The object must be moving at a constant speed, and there should be no changes in directions. Using this, we will compare experimental and computational models based on fundamental physics principles. Now let's look at some fundamental physics principles. Newton's first law states that an object that is in motion tends to stay in motion unless another external force acts upon it. The same could be said for an object at rest. Newton's second law states an object's acceleration is directly proportional to the net force and inversely proportional to its mass. For this lab, constant velocity states that the net force acting on the ball must be equal to 0. Let's look at some important formulas that can go with this lab. The first one is the velocity update formula, which states that the final velocity is equal to the initial velocity plus the net force times change in time over the mass. The position update formula states that the final position is equal to the initial position plus the average velocity times the change in time. It is important to note here that both formulas are derived from Newton's second law. Now we can compare the methods between the experimental and computational models used in this lab. For the experimental methods, a softball was rolled and a short video of the motion was recorded. The tracker software was used to analyze the motion of the ball using position and time stamps. In the experimental model, the system was the softball and the surroundings were the push force and the gravity, as friction and air resistance were not to be included in this lab. As for the computational methods, I used GlowScript to write a code that models the initial state of the ball along with any forces acting on the ball to predict its motion. For the experimental method, I used this video of the rolling softball and tracker to track the motion of the object by plotting its position as a function of time. The softball is rolling from right to left. I chose my axes so that the softball was at the origin, and the right side was positive and the left side was negative. Therefore, the resulting slope of the graph of position versus time was negative, as seen in the top right corner of the video. It should be noted that I set my t equal to 0 to the 31st frame of the video, as that is when the ball entered the frame. To start with the computational method, here's a small portion of my GlowScript code that has the initial conditions. The mass of the ball was not changed for this code because it would have no effects on the physics of the problem according to Newton's second law. The initial position was set to 0, 0, 0, and the initial velocity was set to negative 1.739 meters per second. The initial velocity was calculated using the first 4 frames in tracker, seen on the left on the PowerPoint, and using the average velocity formula as shown below. 1/10 of a second appears to be a good estimate of the average velocity for this experiment. Because I changed my time to match the 31st frame, t still equals 0 and delta t is equal to 1/30 as the video frame rate is 30 frames per second. This next section of code is where the fundamental physics principles we discussed earlier are applied. Because the velocity was supposed to be constant, Fnet right here was set to 0, 0, 0. The velocity and position update formula were also included in this section of the code. Right here. Because Fnet is equal to 0, we can see the velocity update formula will result in the ball's final velocity being equal to the same as the initial velocity. This demonstrates the constant velocity we were looking for in this experiment. The ball's final position also comes down to the velocity of the ball times delta t due to the initial position being 0, 0, 0. Next, the two datasets from the experimental and computational model were added to the same graph of position versus time. The data is very similar for when delta t is small, but as delta t increases, the data begins to diverge. Although it may be hard to see, the computational model remains completely linear, while the experimental model does show some deviations in linearity. This is indicative of the computational model maintaining constant velocity while the experimental model does not. This also means the net force of the experimental model is most likely not 0. This could possibly be due to friction. Get some discussion questions. The first question asks what would happen if we were to flip the x and y axes. I chose the axes so that the right side was positive and the left side was negative. If I were to flip this, the graph of position versus time would have a positive slope versus the negative slope that I have now. The results would mean the same thing, that velocity remains constant, and the sign of the slope would not change any conclusions made in this experiment. The next question states that the computational model predicts our observations well when net force is equal to 0. Is it possible to say how many pushes and pulls / how many forces are added together to give 0 net force? The answer to this is no, because it is virtually impossible to know in our experimental model how many forces are actually acting on the object. It is very hard to guarantee a constant velocity from a human pushing the object, as the push may cause acceleration while friction can also cause deceleration. There may also be other forces like air resistance and impurities on the floor. To conclude this experiment, some possible sources of error may have been the shape of the softball or the floor, which may have caused erroneous accelerations or decelerations that cause a constant velocity to not be maintained. Also, the tracker software may not be perfect in measuring distances and time based on calibration and video quality. Thanks for watching.